Okay, so we'll go ahead and start Module 3 now. And so this is oxidation state 2 and 3, functional groups of oxygen and nitrogen. So you see there's a lot of them listed here. We'll start with aldehydes and ketones. Today we'll look at acetals. Imines, enamines, and aminals will be next week. And then we'll get into carboxylic acid derivatives. So as we go up in oxidation state, that's when we have a lot more versatility with the reactions we can run and the things we can make using these synthetic sequences. Any questions before we begin? So we'll start with nomenclature and physical properties of aldehydes and ketones, and then review some of the reactions we learned in the prior modules of them, and then get on to the new reactions. So aldehydes will always have this CHO bonding pattern. So again, R is the rest of the molecule, and then the aldehyde CHO is by necessity at the terminus of the carbon chain. So the carbonyl has an H and a carbon bonded to it. The nomenclature, you take the parent chain of the alkane, you drop the E and add Al, that indicates aldehyde. So we see, looking at the chart here, going up in carbon count, methane becomes methanal. A lot of these are still referred to as just common names, so that's formaldehyde. Ethanal is called acetaldehyde. And the molecular weights increase because you're adding successive CH2 units, so that's what we've seen for homologs. The melting points are all pretty low, but then you see we get into about room temperature. Formaldehyde itself is, I don't know why I have that dash there, but formaldehyde is a gas at room temperature. Acetaldehyde is a low boiling liquid, so you can actually get it as a liquid form. And then once you're there, you can, sort of use graduated cylinders, etc., to measure those out. The last one is benzaldehyde. You might see that in the lab for 256 at some point. Benzaldehyde smells like almonds. It's pretty strong smelling. So the aldehyde group cannot be part of a ring. Again, it has to be sort of in an aliphatic chain. So when it's when there's a ring attached to it, basically you then use this suffix of the name carbaldehyde. So for the 3, 4, 5, and 6 membered rings at the alpha position. So the alpha position is the carbon next to the carbonyl. If that's a ring, you just put the ring size and then the word carbaldehyde. One thing in regards to nomenclature, the carbonyl group is oxidation state 2. Nomenclature rules state that the parent functional group is based on oxidation state. So if you have a higher oxidation state than 2, then the aldehyde is named as a substituent called formyl. And again, that comes from formaldehyde. So formaldehyde is, again, that 1 carbon unit. And if it's a substituent or derivative of that, it's called formyl. So if we look at these cases shown below, we see that they all have a carboxylic acid. And again, that's oxidation state 3. So that gets priority in the naming. And so the aldehyde, which is oxidation state 2, is then a substituent. And so this first one would be called 3,4-meal pentanoic acid, 2,4-meal cyclohexane 1-carboxylic acid, and then 2,4-meal benzoic acid. So you just have to pay attention to, for example, on this problem here, what is the parent functional group? So in the example, 4-bromo, 2,4-meal, 3-hydroxybutanoic acid, so that has one of each, basically. The butanoic acid is the parent. So if we're to draw out that structure, so there's the numbering of the chain. In blue is the oxidation state, so carboxylic acid is the highest, so that's why it's the parent. And then from there, you just draw in the rest of your substituents. So carbon 4 has a bromine. That means that oxidation state is 1. Carbon 2 has the 4-meal group. So that carbon's oxidation state was 2. And then carbon 3 has an alcohol. And so its oxidation state again would be 1. So the prioritization of functional groups is based on oxidation state. And then you just have to know how to convert that substituent into its proper name. So like bromine becomes bromo. Again, the aldehyde becomes 4-meal. The alcohol is hydroxy. So the CHO group, you can be pretty confident in 3 of these spectroscopic techniques that you'll see it in the molecule. IR, which we'll see on the next slide, has these 2 signature peaks. About 2750 wave numbers is the CSP2H stretch. And then you'll also see the carbonyl stretch between 18 and 1700. So you always have to look, when the carbonyl is the easiest to spot. But with all the carbonyl functional groups, you still want to look around the CH stretching to see if there's an aldehyde. Proton NMR is also indicative because really in the region between 9 and 10 is where that CH will show up. So that's sort of its own unique thing, is if you see something there, it's probably an aldehyde. And then your carbonyl carbon of the aldehyde is between 180 and 200 in the C13. So here is butanal. So 4-carbon aldehyde butanal. And then as shown in region 1, there's that CSP2H stretch. And then region 3 is your normal looking carbonyl stretch. So really those 2 things immediately tell you, okay, part of this molecule has that aldehyde in it. So as we saw before, that the carbonyl oxygen is delta minus, and the carbonyl carbon's delta plus. So carbonyl groups undergo nucleophilic addition, and we saw that when we were taking aldehydes and ketones down to alcohols using organometallic reagents. And so remember, organometallic reagents were strong reagents. So I'm just going to say R2 metal. So that's called an irreversible addition, which means once that organometallic adds, it's not going to go back to the starting materials. And that's, again, because we have a strong nucleophile. As we'll see today, we're going to look at a class of nucleophiles that's weak, and the reactions can be reversible. So you'll get a portion of product, a portion of starting material, and you can affect the equilibrium somehow, for example, using like Le Chatelier's principle. The aldehyde carbonyl is only a hydrogen bond acceptor, so they'll have some miscibility in water due to that H bond. And as you increase the carbon content, they become more lipophilic at that point, and so they're less soluble in water. Compared to alcohols, aldehydes will almost always have a lower boiling point, again, because they're not hydrogen bond donors. So ketones now, the carbonyl group is flanked by 2 carbons. And so if R1 is equal to R2, then it's a symmetric ketone. But if they're not the same, then it's non-symmetric. And as we see in the carbon count, you get to a point where you actually have to specify where the carbonyl is. So for the first one, 2-propanone, you don't really need to specify the 2, because if it is a ketone, it has to be on carbon 2. Butanone is the same way. If it's a ketone, it's going to be on carbon 2. But when you get to the 5-carbon count, here's an example where you can have a symmetric or non-symmetric. So the non-symmetric would be the 2, and then the symmetric would be the 3. So in the non-symmetric example, you have a methyl group and then a propyl group bonded to that carbonyl. In the symmetric, it's 2 ethyl groups. For aromatic ketones, these typically have common names. So if you have the aromatic part, and then based on the number of carbons on the other part, that's where these names come from. So like the ACT, that sort of means 2 carbons. We know from propane that means 3, so propiophenone would have now the 3-carbon chain. So most of the aromatic ones have that type of nomenclature. So ketones can be cyclic. So here we have 3, 4, 5, and 6 as examples. And so you take the ring size and you add ONE. Again, that means ketone. So cyclic ketones will always have 2 degrees of unsaturation, 1 from the ring and then 1 from the pi bond. So that should say ketone, not ether. Ketones, you'll see the carbonyl stretch from 18 to 1700. But what is tricky with ketones is that that's sort of the same region you'll see for esters as well. So an aldehyde is kind of easy to spot. Carboxylic acid is easy to spot. Amides, their carbonyls are below 1700. So ketones and esters are sort of the tricky ones. Your carbonyl, again, the same region, 180 to 220. And really, if you're trying to eliminate the possibility of an aldehyde from the IR, notice in region 1 that there's no CSB2H. So you can say, okay, this has to be either an ester or a ketone. Region 3, the carbonyl, that's your normal region. If we draw this down, there's 1700 at the line. It's above 1700, so it's not an amide. Same deal with ketones as well. That carbonyl carbon is polarized, and we got that based off electronegativity. Low molecular weight ketones like acetone, they'll be miscible in water due to hydrogen bonding. But again, they're only hydrogen bond acceptors. And you'll get to a point where you have enough carbons in there that it's really no longer water soluble. Any questions so far? So these next couple slides are reactions that we studied in Module 2, I believe. So oxidation reactions, a primary alcohol with the Des-Martin periodinane will give you an aldehyde. Basically, any primary alcohol under these conditions, Swern or pyridinium chlorochromate, give you the aldehyde. And then way back in the spring, we learned about taking an alkene. So the alkene must have at least one hydrogen bonded to the sp2 hybridized carbons. And then if we treat that with ozone gas and dichloromethane, and then we add a reducing agent like triphenylphosphine, again, what that does is it cleaves the double bond so that each carbon gets a carbonyl. So we would end up with two different things here. So the 2-carbon aldehyde and then the 3-carbon ketone. So again, that was called ozonolysis. So lysis means cleavage, ozone is O3 gas. If you, again, go on to biochem, you'll see that word lysis a lot. A lot of enzymes are doing cleavage reactions. And again, the majority of the reactions that you learn here in Organic 1 and 2, you're just sort of relearning in biochem, but the reagents are called enzymes. Ketones, to make those through oxidation, you have to start with a secondary alcohol. So for example, again, these undergo that elimination. So you're losing H2 across that C and O, and that's the oxidation. The Des-Martin, Swern, and PCC all do that sort of conceptually the same way mechanistic-wise, but the reagents are just different. And as we saw on the prior slide, if your alkene has all carbon substituents, then again you'll end up with ketones. So since that alkene is symmetric, you end up with two equivalents of acetone. So as we saw prior, carbonyl groups undergo irreversible addition with strong nucleophiles. That means overall they're going through a reduction and they're going to form alcohols. So we saw that in terms of using hydride reagents like sodium borohydride or lithium aluminum hydride. And then the organometallic reagents, so carbon anions with lithium or sodium metal, or magnesium ones, which are called Grignard reagents. So those proceed forward 100%. And so there are reductions from oxidation state 2 to 1. But now what's new for this module is what about weak nucleophiles? And the difference between strong and weak. So that the hydride reagents typically had H-, and then the carbon anion ones, there was carbon minus. So they have that negative charge associated with them, and it's balanced out by some metal. Weak nucleophiles are generally neutral. So things like alcohols, thiols, amines, like those neutral functional groups, they'll still add to carbonyls, but they do it in a reversible fashion. And so the table here shows you the list of weak nucleophiles and then the two different oxidation state 2 functional groups, aldehydes and ketones. So what you really want to make sure you pay attention to is that these weak-ass nucleophiles, they only act on oxidation state 2. Because this module is oxidation state 2 and 3, right now these are only acting on aldehydes and ketones. What is unique about it, it's overall these are not reduction reactions. So in the strong nucleophiles, you had an sp2 hybridized carbon that was reduced to sp3. So oxidation state 2 to 1. But now for weak, sp2 is going to sp3, but the oxidation state is staying the same, which means that for the sp3 hybridized carbon, you're now getting 2 sigma bonds to a heteroatom. You no longer have the pi bond. So here's some new words for you in terms of nomenclature. If you're using an alcohol, that reacting with an aldehyde forms an acetal. If it reacts with a ketone, it's called a ketal. A primary amine forms an aldimine. So there's A-amine and I-imine. So aldimine or ketamine. Now, it doesn't matter what class of alcohol you use. You always get an acetal or a ketal, but for amines, the class matters. A secondary amine will form an enamine, and really what that is, it's an alkene with an amine attached to it. And the same goes for a ketone. So those are enamines. So nitriles like potassium cyanide, even though that carbon is negatively charged, it's considered a weak nucleophile. So when that adds to either aldehyde or ketone, that forms something called a cyanohydrin. Cyano is cyanide, hydrin is alcohol. So it's a carbon that has an OH group plus a nitrile group. Thiols are just the sulfur variant of alcohols. So they form thioacetals or thioketals. And then water, which we know is H2O, that forms what's called a hydrate. So just as the name implies of a carbonyl, you're formally adding H2O to that carbonyl. And that's a hydrate. So most importantly, you're conserving the oxidation state 2, even though the hybridization is changing. So in this example, we have 2,2,2-trichloroacetaldehyde, and we're mixing that with water with an acidic or basic catalyst, and I'll show the mechanism on the next slide. But what I want to point out here is, at oxidation state 2 of the carbonyl highlighted in blue, that's sp2 hybridized. When we form the hydrate, that blue carbon, it still retains oxidation state 2, but now it's sp3 hybridized. So another thing just to point out, again, because it's sp3, it has tetrahedral geometry. And down the road, for biochem or cellular and molecular biology, when you're studying enzymes and metabolism, they'll talk a lot about tetrahedral intermediates and why those things are important as things go through these metabolic processes. So that's forming this molecule called a hydrate. In the nomenclature, you see it's called a 1,1-diol. And there's a gentleman here with a bodacious mustache. Does anyone know who that is? If I remember correctly, since I'm not teaching from PowerPoint, normally it's in a note, but I don't have those notes here. I think his name is Mickey Finn. Have you ever heard that? Like slip someone a Mickey? So I think he was a bartender, and this molecule here, if you put it in a drink, it's basically like it knocks someone out. So you slip them a Mickey, and what he would do is pour that in their drink and then rob them, steal their money. So that form of that molecule with the hydrate and those chlorines is, I don't know what you would call that therapeutic-wise, an anesthetic maybe or something. Or if you're really ballsy, you pour it on a dirty rag and shove it over their mouth and then take their wallet. So that's a hydrate. And so on the next slide, we'll draw the mechanism under both acidic and basic conditions so that you get used to seeing how really what's important is, I'll say PT, so proton transfer. So you're under acidic or basic conditions, and really what you're doing is just shuffling protons around. And if you're comfortable with doing that in this class, when you start learning about enzymes in other classes, that's essentially what the enzymes are doing. They're activating functional groups, they're shuffling protons around so that you can form or break bonds. So for acidic conditions, so we're just going to use hydronium as just the general acid. So notice hydronium is positively charged, so any intermediate we show has to be plus charged. So if hydronium is an acid, the carbonyl oxygen will be the base. So that's going to get protonated. And again, the equilibrium arrows are indicative that, sort of you're forming all of these things, they're present in some amount. You can favor the equilibrium by altering, adding reagents, distilling out the product, that sort of thing. So now we have carbonyl protonated. We can show a resonance form that helps us understand why that second oxygen attacks. So if you look at where we're at, we have an OH. We need to get another OH in there. Since that's positive, we know water, oxygen has 2 lone pairs, so that will attack that. So now notice the plus charge is migrated over to that oxygen. And so to get to where we need to go is a final proton transfer from water. So water acts as a base. And then that regenerates the hydronium catalyst. Again, if you are proceeding on into biochem or these other classes, my strong advice to you is always write out these mechanisms with proton transfers, because again, enzymes are made up of amino acids, and all they're doing is these functional groups are helping shuffle these protons around. So as we saw there, oxygen was plus charged throughout. If we're under basic conditions, say with sodium hydroxide in water, again, you still end up with the same product. But now the mechanism's a little different because hydroxide's negative. The sodium is there as a spectator ion to just balance out the charge. That negative will attack the carbonyl. We break the pi bond, and now the negative is on that oxygen that was the carbonyl. And so you can see we're almost there. We do a proton transfer from water to that alkoxide. that will form the product and then regenerate the sodium hydroxide as the catalyst. So, I mean, there's, the step here, hydroxide attacking, that's your nucleophilic addition. And then the last step is your proton transfer. So water will form hydrates. Derivatives of water are alcohols. So instead of having like OH, now you have OR. And so these are either acetals or ketals, depending on what you're starting with. So butanal, when treated with methanol under acidic conditions. So methanol is both a reagent, meaning it's getting into the product, but also it's the solvent, so it's used in excess. And that is what helps drive the equilibrium towards the product. So a way to think about this, I've highlighted in blue the carbonyl. The H in the rest of the chain, they don't change. The only thing that's changing is what's bonded to that blue carbon. And so you'll notice from the reagent methanol, you're adding that OCH3 twice. So they're both at oxidation state 2, and the reason that this is important, the acetal will not undergo any further nucleophilic addition. So we think of it as, because the oxidation state stays the same, it's a functional group equivalent that's inert to further reduction. So that said, both acetals and ketals are acid sensitive. So if you wanted to reverse this reaction and go the other way, you could unmask the acetal by treating with, again, hydronium ion, but now you would use a huge excess of water. And if you draw that reaction out, just the reverse thing's going to happen. So I'll call that unmasking. So I'll show this as well, so you can see that at some point you're going to get to something called a hemiacetal, and I want to demonstrate to you how you get the OH group to leave, and then you get that other methanol group to attack. So we have methanol plus acid. Same thing as before, the carbonyl gets protonated. So in that forward direction, I'm showing, once it's protonated, there's a molecule of water in there. The resonance form shows us that the carbon is now positively charged because we're using methanol as the solvent. That's the weak nucleophile that attacks. So that intermediate with that plus oxygen is called an oxonium. So OX, onium. Onium typically means a positively charged species, and ox means oxygen. So we can have water act as our base to do the proton transfer. So notice again now at this stage, it's still oxidation state 2, the hybridization has changed, but how do you get rid of that OH? Because we're under acidic conditions, we have to use that hydronium again to protonate that. So what will happen now is an elimination where the other oxygen that's bonded to the methyl group, so that's going to push out water. So I'm running out of room here. I'm going to draw a line. And so another molecule of methanol attacks that. So I'm a very bad artist. I'm not using the entire space here. Things are getting cramped. So that oxygen was protonated. Water will do the proton transfer, and that's how you end up with the acetal. So PT. Hopefully you can read that scribbling in there. So again, what's different here is you have to push out that OH, which at this point, when it eliminates, it's lost as water, which is neutral. If you look down here, you can't have this push out because that would generate hydroxide. And you can't do that in the presence of hydronium. So if you first have to protonate, and then you can do your elimination. And what I might point out before we move on, you see the product here. If you want to go the reverse way, you're just swamping it with water and hydronium. One of these oxygens gets protonated to this. The other oxygen will then push out methanol to go this way. And then you're just reversing it. You would have water attack there. you do a proton transfer to get back to here, and then this would get protonated, and then you could eliminate out another molecule of methanol. So these operate under equilibrium, where you're controlling that through either the amount of solvent as the alcohol, or you're adding water to get it to go the other way, or if you get real fancy, what people will do is, as the product is formed, if the boiling point is sufficiently different, you can distill it out, and that drives the Le Chatelier's equilibrium. Another useful variant of this, so two things on this slide. The first is you're using a thiol, so that's RSH. And the other thing to point out, I'll highlight in blue, notice that the thiols are connected. So if your alcohols are connected as a diol, that necessarily means you're forming a ring in the product. So again, the blue carbon, sp2, the blue carbon here, sp3. So that blue carbon is one atom. Overall, you're sort of doing a dehydration. So anything that's connecting those two S's comes along for the ride, and you're forming ultimately a ring. Since that's 4 atoms plus the blue one, you get a 5-membered ring. And that's called a thioacetal. And the reason that these are special as opposed to the oxygens, thioacetals can be fully reduced. So that oxidation state 2 can go to 0 when you treat with hydrogen gas. And then this nickel catalyst, it's called rainy nickel. And so in the strategies and tactics for organic synthesis, that's useful for, if you're doing other manipulations, but you ultimately want to get rid of that oxidation state, this is a way to do that. Okay, so over the next couple slides, we'll sort of put that into practice where we look at these different oxidation states, and we'll see that we have an issue when we get up to oxidation states 2 and 3 with some of the reagents that we've already learned. And if we want to selectively act at one position versus another one, how can this chemistry help us? So when we were using iClickers, I think basically you had to come up with like a sequence of letters that would represent these steps. But the issue here, as I'll write in blue, you have a ketone at oxidation state 3, an ester at oxidation, or a ketone at oxidation state 2, and ester at oxidation state 3. And you want to make this product where the carbonyl of the ketone's retained, but the ester's been reduced to 1. The issue is sodium borohydride only acts on aldehydes and ketones. Lithium aluminum hydride acts on both. So if you just treat that with lithium aluminum hydride, the product that you would get would be this. And now you're sort of screwed because you have a primary alcohol, a secondary alcohol. You can't selectively oxidize the secondary one back up to the ketone. So you have to use a whole different strategy where you protect the ketone first. And so that would be step 1 would be E. That would get you to the, what are we using? So methanol. That would get you to the ketal, which is still the same oxidation state, but now you can treat with step 2, lithium aluminum hydride. Which will reduce that. And then finally what you do is just unmask with the 3rd step. And that's D, where you're using water as the solvent to push the equilibrium towards the carbonyl. And so these are strategies that chemists use to work around dealing with these different oxidation states. And this is an example of using the thioacetal, where in your starting material, your carbon number 3 is at a ketone oxidation state. Then in your product, you're reducing it down now to 0, which is the alkane. So the first thing we want to do is find the reagent with the thiol. So that would be J. And then once we have the thioacetal, step 2 would be the rainy nickel with methanol, so that would be entry C. And then that reduces that oxidation state fully down. So again, oxygen-based acetals do not do that. Only sulfur, and the difference is sulfur is in the next row below oxygen. So presumably because it has access to d orbitals, it can do that chemistry. I think maybe we'll skip this slide. This is another example of that strategy. The blue carbon is the carbon that you want to retain oxidation state of 2. And then maybe with green, you want to reduce those esters down to alcohols so that the alcohols can cyclize onto that ketone. So it gets a little steppier. Again, step 1 would be your protection step. So that would be F. So that protects the ketone as the acetal. Then step 2 would be B, which is your reduction of the esters. And then the last step would be E, where you're treating with water and an excess of water and an hydronium. So that's the product of step 1. Step 2, you get your alcohols. And then what happens in step 3 all at once, the acetal or ketal is deprotected, and then those waters then cyclize back on it. And there's a lot of like natural products that come out of like marine sponges that have these acetal linkages in them. So this area of chemistry is pretty important for making those type of molecules. So I think the last 3 slides here, we've talked about water, alcohols, thioacetals. The last weak nucleophile for today is cyanide. Shown here is sodium cyanide, but again, since it's just M plus, Cn minus, M can be lithium, sodium, or potassium. Probably the most common is potassium cyanide. So an aldehyde plus sodium cyanide, we use this shouldn't say base, this shouldn't say acid, it should say base. With cyanide, we don't use acid because that generates HCN. The metal cyanides are all solids. They're easy to handle. You can weigh them out. There's really no issues. HCN is a gas, and so it will kill you pretty quick. So all of these are run under basic conditions. We use water to solubilize the cyanide, ethanol to solubilize the aldehyde, so that's the biphasic mixture. And what you notice in the red numbers, your aldehyde at oxidation state 2, it's actually reduced to oxidation state 1, and this was that cyanohydrin. So it's technically not retaining the oxidation state number, but if you look at that cyanide carbon, it's at a higher oxidation state. So you're basically forming 2 things, an alcohol plus a nitrile. And the benefit of that is you've got a carbon in there at oxidation state 3, which is functionally equivalent to a carboxylic acid at oxidation state 3. the aldehyde just initially undergoes a nucleophilic addition. So cyanide's the nucleophile it attacks. So we've seen that. And then we just get a proton transfer from water. So as I said, that's oxidation state 3, which is functionally equivalent to a carboxylic acid. So cyanohydrin or alpha hydroxy nitrile. And so our last slide today just shows you that equivalency, that you can take the nitrile and hydrolyze it. You typically have to use forcing conditions, and really what that is you have water at its boiling point or above. So either under strongly acidic or strongly basic conditions, the nitrile is unmasked to the acid functional group. And so the tie-in to the rest of the module is you have oxidation state 3. And then really what we'll learn is all the derivatives. So the acid is sort of like the parent. From that, you can make esters, anhydrides, acid chlorides. You can take the acid back to the nitrile. So it opens up your sort of mind map of reactions in how you can move from one functional group to the next. Any questions? I think that's the last slide for today. So your quiz today will be due Monday at 1. Don't forget about it. I know I'll check Monday morning and like 6 people have done it, but don't let it slip away. On Monday, what we'll look at is amine nucleophiles to form those functional groups. And those are the ones that are really important for biochem, because biochem uses imines and enamines to do a lot of bond-forming reactions. And then I think next Wednesday we'll get into oxidation state 3. Your exams have been graded. You can see the pictures in ZipGrade. I don't think I've uploaded the scores yet into Canvas, but I'll do that today or tomorrow.